Hi, I'm Marcus, and today I'll be showing you how to visualize a phylogenetic tree using a rectangular rooted layout algorithm. This will produce clean drawings of phylogenetic trees that look something like this. This video assumes you have some familiarity with graph theory and with trees. In biology, we often use phylogenetic trees to represent evolutionary relationships between organisms, or other sorts of hierarchical relationships. You may have seen trees used in recent literature to represent the evolution of different strains of SARS-CoV-2, the virus that causes COVID-19. It's very useful to be able to visualize or draw these trees in order to make life easier for biologists studying this data. The algorithm we'll discuss today is one of many methods for drawing phylogenetic trees. It's similar to many of the rooted tree layout algorithms described in Chapter 34 of Felsenstein 2004. Now, let's review some terminology we'll be using within this video. Trees are hierarchies, so we often say that a node in the tree is a parent if it has at least one outgoing edge to another node, and that node is the child of that parent. We allow nodes to have any number of children, so unlike a binary tree, a node could have 0, 1, 2, 3, or more children, instead of being limited to 0 or 2 children. Usually, the tip nodes of a phylogenetic tree, that is the nodes without any children, correspond to species. These are shown here. And the internal nodes of this tree, that is nodes with children, usually correspond to common ancestors. These are shown here. One of the important things to note is that all the edges between nodes have lengths. These lengths must be non-negative. In the context of a phylogenetic tree, the lengths usually correspond to the time taken between events. So having a negative length doesn't really make sense. We can think of this as that the tree must flow along one direction. This is also because the tree is acyclic, so of course it can't go backwards. Okay, so we'll start with any sort of phylogenetic tree. These are often stored in a computer in something like a Nuig file, and trees can be represented in memory using various data structures. Here, we'll gloss over the details of the implementation. We assume that you have the ability to access each node of the tree. That's all we're going to need. The example tree we're going to be working with today looks something like this. During this algorithm, we'll need to keep track of a few things. One of these is a mapping of nodes to their x and y coordinates. Depending on the language you're using, this may be called a dictionary, an associative array, or an object. For now, we'll just draw this on the tree as we go through it. Another thing we'll need to keep track of is a numerical value. We'll call this next y, for reasons which should become clear soon. For now, let's set next y to 0. So there are two main traversals of the tree required for this algorithm. The first of these is a post-order traversal. What this means is that we start at the root node of the tree, and then recursively visit the child nodes of that root node, and then only after visiting all descendants do we visit the node itself. The reason we do things this way is that this ensures that for every internal node within the tree, we visit all the tips below it before we actually visit the node itself. This post-order traversal will be used to assign y-coordinates to nodes. The exact order in which you visit the child nodes of a given internal node is arbitrary. So as we do this post-order traversal, and as we visit the nodes in the tree, we'll do one of two things based on whether the node we're visiting right now is a tip or not. If this node is a tip, then we should assign this node a y-axis value of next y, and then increment next y by 1. If this is not a tip, then by definition we have already assigned y-coordinates to the tips below this node. In this case, we assign this node a y-axis value of the averaged of its child y-coordinates. The final node we visit in the post-order traversal will be the root of the tree. Once we assign this node a y-coordinate, all nodes will have y-coordinates assigned. Now we need to assign x-coordinates to nodes. We'll do this using a pre-order traversal, which works in the opposite way from post-order traversal. We first visit a node, and then we visit its children. We start at the root node of the tree. Depending on whom you ask, it may or may not make sense to draw an edge leading to this root node of the tree. Here we won't bother with that, but you could of course add this in if you so desired. Anyway, we start at the root node of the tree, and we place it at x equals 0. Next, we go through the root's children, and place them at x equals 0 plus the length of the edge leading to this child. We then go through the children's children, and place them at x equals parent x plus the length of the edge leading to this child. By going through the tree in pre-order in this way, we ensure that when we visit a node, to assign an x-coordinate to it, we've already visited its parent. This lets us push nodes based on edge lengths arbitrarily deep. At this point, we've assigned x and y coordinates to every node in the tree. We're almost done. If we draw out the tree with these coordinates, we get something like this. So, although we have pretty much every coordinate we need for the tree, we still need to be able to draw vertical lines that connect the children of each internal node and show the sort of span of this internal node along the y-axis. Fortunately, doing this is pretty simple. How we can do this is just for every internal node, figure out the minimum and maximum y-coordinate of its children, and then draw a vertical line between these coordinates. For internal nodes with just one child, we don't bother drawing a line. Alright, so that's it for today. That was a pretty fast walkthrough, but hopefully you got a sense for how this algorithm works. As mentioned, there are a lot of different ways to do this. If you're interested in learning more, I highly recommend checking out Felsenstein 2004 for a lot of details on phylogenetic trees and drawing them and other things with them. Thanks, and have a nice day.